What was the fourth axiom for the inner product? Yeah, it was what? Was it x with x is greater than 0? Yeah, that last axiom is not, it's not included in the symmetric bilinear form. That last axiom is sometimes called positive definite. So if you have a positive definite symmetric bilinear form, that's the real inner product. That's kind of a nice efficiency in concept. Complex inner product, no such luck, because we don't have bilinearity for the complex inner product, right? Because we can't pull out complex scalars in the second thing. It's so-called sesquilinear. It's not quite this. Is there any other one of these that particularly attracts your attention? No? Yes? Oh, how about this? Part 4, we're supposed to show that the usual basis for symmetric matrices is an orthogonal basis with respect to the Frobenius inner product. How would we actually... Oh, that's no fun. I don't want to do that one. Let me look at 7. 7 might be useful for you guys. Trying to do something a little bit less abstract here. Last couple minutes. Something with numbers. Hey, these were numbers. So 7, we had S equal to 1, 1, 1, 1, 0, 2, 1, 0, and 1, 2, 0, 1, 2, 0, 1. So this is obviously a subset of what? R4, right? Or you could say Q4 or C4 if you wanted to be a jerk about it. I said find an orthonormal basis for span S. And if A, B, C, D is an element of span S, find let me call this thing V. Find the coordinate vector of V with respect to beta for your beta being orthonormal. As I think about this problem now, 2 ways of doing it come to mind. The one way that comes to mind is just to run Gram-Schmidt on the given 3 vectors. One way we could do it. Another way we could do it would be to find a vector which is perpendicular to all 3 of these, and then find a basis for the perp of that. That's a null space calculation. So we can either be sneaky and do a null space calculation, or we can just be boring and do Gram-Schmidt. Let's be boring. So let's, as I've been doing, call this S1, S2, S3, right? So what's S1 prime prime? What's the length of this vector? That is a vector of length 2. Yeah. Square root of 4 is 2. So 1/2, 1, 1, 1, 1. Then S2 prime is what? It is S2 minus the inner product. Well, I can use dot products here, right? So S1 prime prime dot S2 times S1 prime prime, which here is 0, 2, 1, 0, minus, what's the dot product of S1 prime prime? So there's a half squared. I'll just pull the half squared. There's 1/2 from S prime prime. There's another half from S prime prime. So what I'm going to have then, what's still left is 0, 2, 1, 0, dotted with 1, 1, 1, 1. That's, this number times the vector 1, 1, 1, 1. So this is a number. So what's that dot product? Three, right? So we get 3 minus 3/4, 1, 1, 1, 1. So that gives us, minus 3/4. What's 8 minus 3/4? 5/4. What's 4/4? 1/4. Blah, 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 blah. Minus 3/4. You can pull out a fourth. People out there. Minus 3, 5, 1, minus 3. I recommend pulling the fourth out because normalization then becomes easier. So what's S2 prime prime? 1 over the square root of 9 plus 25 plus 1 plus 9 minus 3, 5, 1, minus 3. I don't know about you, but I'm getting tired of this. So I'm going to write it over here. 1, 1, 1, 1, 0, 2, 1, 0, 1, 2, 0, 1. And I'm going to, if I have 2 minutes, I have exactly 2 minutes. Show you the website which does this for you. Although we may need to be a little bit creative because I think the website is set up for a slightly more boring case. And so we may have to manipulate our problem to make it fit the boring case. We can do that. Come on. Yep.
We have a vanishing 1/4.
Yes, if you normalize a vector and normalize 17 times that vector, the unit vector is the same. Can somebody have the lights for me? Yeah, don't make. Yes, the other half of it. Yeah, thank you. No internet connection. Well, suppose you want to normalize 10, 10, 10. You want to normalize 1, 1, 1. What's the unit vector for 10, 10, 10? What's the unit vector for 1, 1, 1? Think about it. If you pull out a 10, in the normalization process, you divide by the length of the vector, which is 10 times the vector, length of the vector 1, 1, 1. So if you can find a scalar product, a scalar to pull out of a vector, you just normalize whatever multiplies the scalar. You don't have to worry about that fourth. It's a trick. I'm sorry, guys. So here, the Gram-Schmidt orthogonalizer right there under, this is our website. Right there, we have, I think we have to do 4 vectors. All right. So what are my vectors? 1, 1, 1, 1, 0, 2, 1, 0, 1, 2, 0, 1. And then I need a fourth vector, which I'm going to guess 7, 6, 5, 4 is not in the span of the first 3. There's the original set of vectors, and here's an orthonormalized set of vectors right there. So that's what we just found, half, 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 half for a first thing. This is what the second one would work out to in a decimal form. And then there's the third. So this is the orthonormalized set of vectors. And if you don't like decimals, you could, find the fractions for those without much trouble, probably. Well, anyway, there it is. Of course, Gram-Schmidt will give you exact fractions and junk if you want, but that is a good way to check your work on a Gram-Schmidt, right? Gram-Schmidt, it's pretty easy to like mess up the arithmetic in like the